Good evening, everybody. Welcome to today's live stream AP51, dealing with momentum, energy, free response questions, and a little bit of everything else. My name is Peter Epps, and it's great to have you guys here. Just a reminder, if you want to check out other streams and stuff like that, at Think Fiberbolt on social media is your go-to place for all that. All right, so we're going to start off with basically any open Q&A, any questions you guys have on momentum, energy, etc., etc. And now all these I'm going to solve in a minute, but these are all old AP Physics B and C questions on there. These are all the mathematical side of momentum. We'll get to the non-mathematical side in a little bit. Dealing with deriving equations, calculating energy, and then calculating the momentum, or vice versa in there. Why harping on this a little bit more than, let's say, the conceptual stuff? A lot of times we can do, if you can do the math, you can do the conceptual parts. And for the deriving questions, for the describing what's going on sort of things, especially with the new AP exam format this year, it probably makes more sense to lean a little bit more towards the math and a little bit away from the conceptual for right now. We'll come back to the other ones later on as we need to. Okay. All right, so let's dive into some free response questions. And if at any time you guys have questions, throw up in the chat, and we'll go from there. So let me get over to my notepad here, and then we will make this work. All right, so there is our notepad. And all right, so question number 1. We've got a block of mass M resting on a horizontal frictionless table and is attached to a spring with a spring constant of K. We have a second block of mass 2m, initial speed of v0, collides with and sticks to, that could be important later on. The first block, we have to develop expressions for v, the speed of the blocks after impact, and x, the maximum distance the spring is compressed, given in terms of the known quantities, mk and v0. All right, so starting off with this, they're definitely cluing us in that there's a collision going on here, which means that we really need to think about momentum first. Momentum, conservation here, there's no friction on the table, which means we don't have to worry about any energy or any momentum being lost or gained here. It's all going to be 100% P before equals P after. And because we're not told anything about the energies or stuff like that going on afterwards, really, for part A, I think it makes the most sense to start with conservation of momentum. P before equals P after. Now, for the collision, we have 2 different objects that we care about. We care about the 2m block, and we care about the m block. After the collision, however, those 2 blocks are now stuck together, so they would have 1 object. So we're looking at 2 objects before the collision and 1 object afterwards. So I'm going to do the momentum of the 2m block plus the momentum of the m block must be equal to the momentum of the 2m plus m blocks. So sticking them together because now they're joined. Okay. So now in this case, we've got momentum of the 2m block. Whoa, pick up the pen. Is mass 2m, speed v0. And for the single m block is 0 because they told us it's at rest. Block of mass m is resting on there. So there's no sort of friction or there's no sort of momentum going on with that at all. Afterwards, we're going to have the masses, they're now combined. That's going to give us 3m moving at some speed, v. And our goal is to find v. All right, so a little bit of math here. The m's can both cancel out. We'll get 2 v0 over 3 is our ending velocity. and that is our final velocity for the situation. All right, welcome, David. If you get any questions anytime, we can definitely address those. We're doing momentum and energy, and kind of work our way through this FRQ. If you've got questions specifically or in general for momentum and energy, we can also pause this and go address those if you wanted to get to. All right, so we did part A, P before equals P after, stuff like that coming through. The next part of this question, or the last part, talks about finding X, the distance the blocks are compressed. So now we're looking for the spring, we're looking for something about the X here. That really is not a momentum part. It could be a forces question, or it could be an energy question. In this case, it makes more sense to do it with energy because I don't know anything about the force pushing on the spring. So for part B, it's going to be easiest to say that I start with kinetic energy and it turns into potential energy in a spring. We have all the potential energy being stored, all came from the kinetic energy of these two moving blocks. So kinetic and then potential in a spring. We jump over to the reference tables, and then we can pull out kinetic energy, 1/2 mv squared, 1/2 kx squared for potential energy in the spring. And we can go through and solve for K. All right, so let's drop the 1/2 to start off with. We'll plug in the values we know here. Our total mass is now 3m. Our velocity is 2v0 over 3 squared equals k times x squared. All right, a little bit of working here. 4v0 squared over 9 times 3m, so that's 4 mv0 squared over 3 is kx squared. And then finally solving for x completely here, 4 mv0 squared over 3k square rooted is x. And that matches all of our requirements. It's in terms of mk and v0. And yeah, that is that question done. All right, so one question down, several to go. All right, so that's the first question here. Question number 2. Let's see if I can make this a little bit bigger here. There we go. So a small block of mass m is released from rest. At the top of the curved frictionless ramp as shown above, the block slides down the ramp, moves with speed 3.5 v0 when it collides with a larger block of mass 1.5 m, which is at rest at the bottom of the incline. The larger block moves to the right at a speed of 2 v0 right after the collision. Show all your answers in terms of given quantities and fundamental constants. So, all right, let's take a look at this one then. This one, we've got a block sliding down, hitting it. That, to me, says we're looking at doing some energy here. So we've got some energy potential at the top, turning into kinetic at the bottom. We're asked to find the height of the ramp first. So to do that, let's just start off with part A here. I'm going to say we have potential energy due to gravity, and all of it turns into kinetic energy as the block slides down the ramp. So our potential energy due to gravity, mgh, and our kinetic, 1/2 mv, I'm sorry, 3.5 v0 squared. Change that, m times 3.5 v0 squared. Okay, because we're told we have that speed at the bottom of the ramp. All right, well, good news is we can drop masses out. We can square 3.5. We can divided by g. And then we're going to end up with, as a result of this, that the height of our ramp is 6.125 v naught squared over g. And let me just double check that because I'm questioning my math right now that I did earlier. So 3.5 squared is 12.25 divided by 2, 6.125. Yep. And there is our answer to part A. Energy, potential, into kinetic, and solve from there. All right. Second part, determine the speed of the small block after the collision. All right. So once again, we're told collision here. We're given starting speed, ending speed, mass of the other block, all sorts of stuff like that. That's how we're going to solve this one. We're going to do momentum. So for momentum, we have P before equals P after. Beforehand, there are two objects I care about, the momentum of the big block and the momentum of the little block. And then likewise, afterwards, I care about both blocks as separate objects. There's no sticking together here or anything like that. So we have to go through and treat everyone individual. So I've got a mass of m with a speed of 3.5 v naught plus 0 because this guy was at rest and didn't have a velocity at the beginning. That must be equal to, okay, so mass m, some speed v, that's what we're looking for, plus 1.5 m times 2 v naught. All right, so we can drop all the m's out because every single turn has one. So we're left with 3.5 v naught equals v plus 3 v naught. That means v must be equal to 0.5 v naught. And because this is positive, we know we're also moving to the right in this case. The question didn't ask it, but it's always good to keep in mind what's going on here. We're not bouncing off. We're not bouncing away. We are just sitting in there and going the other part. In there. So, all right. Part C. The larger block slides a distance d before coming to rest. Determine the value of the coefficient of kinetic friction between the larger block and the surface on which it slides. All right, so this one, we're looking for friction. And friction, to me, is, well, and hopefully to you too, there's only two options here. We're either looking at forces, normal force, force of gravity, that sort of thing, or we're looking at work, non-conservative forces taking away energy. And based on the fact that we've done energy already, and I see no mention of anything in this question that's talking about forces, we're going to do the energy method for that as well. Okay, so for part C, I'm going to say the work done by friction took away all the kinetic energy from that big block. Okay, that 1.5 m block lost all of its kinetic energy because of friction. Friction took it away. So remember, delta would be the final kinetic energy minus the initial kinetic energy. So it's going to come to a stop. So that makes this part 0, which is really easy here. So the work done by friction must be equal to a force of friction times a distance d, and that is equal to negative 1/2 1.5 m 2 v naught squared. So plugging in all of our stuff we're given, 1.5 m for the mass, 2 v naught squared for the speed immediately after the collision. So again, we're using that speed right there. And now we just go through and solve this. So the force of friction is, let's see, so let's expand this about force of friction times the distance will be half of 4 is 2, 2 times 1.5 is 3, so this is 3 m v naught squared. All right, now we can plug in for the force of friction part. This is mu f n d. We're on a flat surface, so really this is mu mgd, and this will equal 3m v naught squared. Just like in the previous example, we can get rid of the m's, and those can disappear. And now we're just solving for mu. So all I really have to do here is divide by the d, divide by the 3, or sorry, divide by the g, and I will get mu is equal to 3 v naught squared over g d. And there's our answer to that one. All right. Yeah. And then that was that part. Finally, on this question, we are asked to indicate whether this collision is elastic or inelastic and justify our answer. All right, so for this, inelastic collisions, we know, this is the vocab stuff we should know. Inelastic means we are not conserving kinetic energy, whereas elastic means we are. So really what we need to do is figure out, is the kinetic energy before this collision and after the collision, is the total going to be the same or different? If it's the same, it's elastic. If it's not the same, it's inelastic, and our justification is basically given by the math in there. All right, so let's work through. Kinetic energy before is pretty easy. There's only one block moving. That's the block M. So this is 1/2 M V naught. Sorry, 3.5 V naught. Squared. And then we go through again, we square it. We get our 6.125 in there. So our kinetic energy beforehand, 6.125 m v naught squared. And now, yes, if I was really concerned about significant figures, I would not have that many digits displayed. But right now, I'm just going to compare them. We'll deal with sig figs and stuff like that if we need to, if we're close enough to make sig figs actually worthwhile here. Okay. Afterwards, we now have two objects we're concerned about. The big block, the 1.5 m, and the little block, which still has some velocity going on afterwards, so it has kinetic energy as well. So this will be 1/2 small block m times 0.5 v naught squared plus 1/2 1.5 m big block times 2 v naught squared. So let's see. A half squared is a quarter, half of a quarter is an eighth. What's an eighth of a fraction? It's going to be 0.125 mv naught squared plus, let's see, half 2 squared is 4, half 4 is 2, 2 times 1.5 is 3 mv naught squared. So we get 3.125 mv naught squared is our kinetic energy. Afterwards, those two things are not the same number, right? This does not equal this, which means this is inelastic. there. And now some of you guys may be wondering, well, what happened to that energy? Where'd it go? This could have gone into sound energy. It could have gone into thermal energy or heat. It could have gone into jostling them in a direction that's not linear. It could be sound energy. The big idea here is it's not kinetic energy anymore. It's deformations, maybe from running into each other. That's where the energy could have gone, but it's obviously not in that either one of those blocks as kinetic anymore. Okay. All right. Other things here. We'll take a break for a second here. All right. Well, let's continue moving on here. This one bigger. All right, so this one is an experimental design question where we've got a dart going in there, and we're having a dart run into a pendulum, or a massive swing up like a pendulum going on here. Okay, so we have a bunch to figure out, and it looks like we got an experimental part of this too, which is good because we know there's probably going to be an experimental design question on the FRQ parts of this year's test, so extra practice doesn't hurt there either. All right, so we have a dart hitting a block. Oops, sorry. A dart hitting a block down here. That block then swings up to its final position with the dart stuck in it. So this is the dart and the block stuck together. Size of the blocks negligible compared to L, blah, 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 blah. Okay, so let's tell our answers in terms of M, M naught, L, theta max, and G. Part A, determine the speed being out of the dart immediately before it strikes the block. Okay, well, so we know the dart and the block collide. So there's a collision here. This looks like momentum. And then it swings up higher. This looks like energy. So it looks like the game plan here is to find the potential energy we reach at the highest point, backtrack that into kinetic energy, and then once we have kinetic energy, we can get velocity. From velocity, we can do P before it goes P after, and then get our momentum of the dart beforehand. That sounds like a lot. But let's see how we do. So we're going to start here and do potential energy came from kinetic energy. So this is M plus M naught G. I got to find height. I have to find this difference in height. And to do that, that looks like it's going to be, well, my height here is L away from the ceiling. At this part, it's only L cos theta, which means that our difference in height, our change in height, must be L minus L cos theta. And that must be equal to our 1/2 M plus M. Pan for a second here. There you go. M plus M. Come on, grab the marker. M naught V squared, where V is what we're looking for here. All right, well, looks like some good news. Those masses are the same. They can disappear, which is good. That's really good, actually. So we're going to get our velocity is going to be, let's see, 2, because I'll multiply by the 1/2, G L 1 minus cos theta, all square rooted. And there's our velocity after the collision. Now, that's good. We're only half done now. We need to find the velocity of the dart before the collision. immediately before it strikes is what we're looking for here. So right before it strikes the block. Okay, well, we've done the energy part already. We've done this part. Check it off. It's done. Now we're getting momentum. So I can say P before equals P after. So I've got the mass of the dart, which is little m, times, let's call it V naught. So I guess that's a good term to use for the original velocity, plus 0. The block isn't moving anywhere, so I don't need to worry about it. That's equal to m plus m naught. So the block and the dart's mass is added together, times the square root of 2gl 1 minus cos theta. And okay, let's just divide by little m, and we're done here. So the velocity of our dart is m plus m naught over m times the square root of 2gl 1 minus cos theta. And there's our speed of the dart before the collision. Okay. So in this case, this was a good example. We used energy to find speeds, and then use speeds to find momentum. Kind of the opposite of what we did last question, where we used momentum to find the speed to find the energy. Here we're working backwards. All right, part B. The dart and block swing as a pendulum. Determine the tension in the core when it reaches the lowest point in the swing. All right, let's make a little work there. Okay. So with this, yeah, let's draw it out. So I've got my block up here attached. It's going to swing down through and back up. I'm looking for the tension at that lowest point. All right, well, if the block's at the lowest point, there's my string. How many forces are acting on that block? Well, there's 2 of them. We have gravity going down, and this would be m plus m naught, so both objects, times g. And we have the tension of the string pulling upwards. So this is actually forces. We're looking at some sort of F equals ma sort of problem here, because we're dealing with tensions and stuff like that. So let's do that. Let's look at part B. Let's do F equals ma. Well, we know we got to be swinging in a circle, and this is circular motion. The tension going up must be bigger than the weight pulling down. Okay, so the vertical tension going up must be bigger than the weight going down. So this is T minus m plus m naught g equals m plus m naught a. All right, well, that lets me put tension in here. Tension must be the mass is times g plus a, but we're going in a circle. Acceleration in a circle is v squared over r. So this is v squared over L in this case, because L is the length of our radius. And now we get to just plug in. We know what v is. We know what the speed was before we collided. Let's plug that in. And then simplify, and then we're good. So this will be tension equals m plus m naught times g plus all this wonderful stuff. all this wonderful stuff squared. All right. So plugging all that stuff in. So it's G plus M naught over M squared 2GL 1 minus cos theta all over L. Yuck. This looks like it's just a mess. Good news is L can disappear. Can I do much more with this? I am not quite sure. Oh, crap. Hold on. Hold the phone. That's the wrong V. I don't want that V. I don't want the V of the dart before it collided. I want the V from way up here. I want this V, the V at the bottom of the swing, not the V of the dart. So no, ignore that. We are not taking this one through here. We're taking that V down there. Okay. So this is the square root of 2GL 1 minus cos theta over L squared. Okay. That is at least nicer math. General rule of thumb, the math here shouldn't be super messy, shouldn't be super complicated, stuff like that. If it looks like you're getting somewhere that's way too messy, it's probably not the right math equation, or like in that case, you're trying to plug in the wrong number. Okay. So continuing on here, tension M plus M naught times G plus 2G 1 minus cos theta. Square it, we can drop the L's off. And then finally, if I really wanted to, yeah, you know what, let's combine stuff. 2G minus 2G cos theta. So T equals M plus M naught times, let's see, this is, I did too much in my head. G plus 2G minus 2G cos theta. So that's 3G minus 2G cos theta. And if we really wanted to, we could pull the G out in front too, but this is good enough for me. Let's not oversimplify, although it's not that hard to do that last step. This is perfectly fine for an answer. We don't need to go any further in that. Okay, and then finally, part C. At our land table, we're also given this set of equipment. Without destroying or taking apart any of the equipment, how else could we figure out the speed of the dart just after it leaves the gun? Okay. So instead of using a pendulum, we're going to use a spring. Well, I guess, yeah, this looks very similar to the previous question we just did. And again, with any experimental design question, this is not the only way to do it. This is simply just the one that I was thinking of right now. So we definitely could find a different one here. My thought is, for this part, let me change colors here. We could take and find the K of the spring by hanging it vertically, putting some mass on it, measuring the change in X for for each of the known masses. do something like graphing force versus delta x. Linear graph, slope of it tells us k. So now we have the spring constant that we have for our chunk, and that would use the meter stick, the masses, and the spring. The next part, once I know k, is we can set this up to have the dart be shot into a block attached to the spring. And let's say we know the mass of this, right? Yeah, so we're going to take one of those blocks, put it on there. It doesn't really matter. Shoot it into the spring, measure this change in x, and then from there you can use potential energy in the spring. Turns in came from kinetic. We find v, and then conservation of momentum to find v naught. Okay. Pretty much exactly like we did in the previous question back here in, not that one, this one. That's where we had a block moving in, hits, it collides, stuff like that. The only difference is that's your dart right there instead of the block of mass 2m. Either way is going to work for that. Okay, so that's one way to do it. Another possibility, since we're doing experimental design, let's talk about a couple other things you could do. You could, what could we do? You could do the same sort of thing. Doing an angle makes it more complicated. That's not something we want to do. What other tools are we given here? We're given a stopwatch. Given a stopwatch, we could just shoot the block, figure out its speed. No, because we don't know. We don't have anything defined, mass or stuff like that. We could. We're not going to reproduce a pendulum because that was what was already done with the string and stuff like that. I wonder if, and this is me just thinking out loud here, I wonder if we could take it, do the same stuff to find the spring constant before. So we're going to measure x with a different mass on there, make our plot, force versus k, force versus x, find k, stuff like that. But now I'm wondering if we shoot the dart into the block and have it start oscillating up and down, up and down, up and down, we could figure out, based on the equilibrium position of that, where everything goes. Yeah, we're doing an energy problem, and you can say that at this position, at our equilibrium position, you will have that dart hit that will give you all the kinetic energy that that system has. So we can say kinetic energy at the equilibrium must come into potential energy in a spring when this goes up to the lowest point, or its potential energy to gravity to the highest point, but I think the lowest one here. So we'll let this go, we'll let this oscillate up and then down to its lowest point. This delta H will let me find, or delta X will let me find potential energy from that. Use the potential energy to find V, and then use V with P before equals P after to find V naught. Other options, just think about, I don't think they gave us enough stuff for it. Oh wow, they did give us a stopwatch. I'm thinking just, do you shoot the dart straight up and do kinematics? Or potential energy turns into kinetic energy. It's got to be kinematics because we have a stopwatch. So you can time until the dart falls back down again. Half that time is when it stops. You know the acceleration is g. I'm liking that one. So another option, we shoot the dart straight up in the air. We measure the time to go up and to fall back down. And when I say ground here, I mean the firing height it was fired at before. So maybe hold it parallel with the tabletop, and then when it hits the table again, is the same height or something like that, and that could work. Okay. At the top, we know our vertical velocity is 0. This is in free fall, so we're going to say our acceleration is negative 10 meters per second squared going down. We could do something like V equals V naught plus AT. So 0 V naught minus 10t. We use half of the time there. So this t is time to go up. T up is 1/2 t total, and solve for V naught that way. Do it many times and then average them together or something like that could work too. But there's another possible method of doing it in there. And if you're really good, you use like the protractor in there. So it says that you're firing at 90 degrees. So you're shooting straight up in the air, not 80 or 70 or something, not eyeballing it, but saying this is exactly the height we're going or the angle we're going at there. All right. So that being said, there's 3 different ways to solve that one. I think all of them work. It's really your personal preference. Now that I thought about it, I really like that third one. But doing the mass on the string and finding K and stuff like that also works perfectly fine. All right. And our last question. This one is another physics C problem on there. We are probably not going to do part D. I'll talk through it, but I think the math is going to get too messy for us to do it as an AP Physics B question in here. But we definitely do part of it in here. So we got a person with rope L, 90 degrees apart. They're going to swing down there, grab a stone, and when they grab the stone, they let go, at which point they fall into the water. And we're supposed to find all these things in terms of M, L, and G. So all this stuff right there. So more deriving sort of stuff. All right, so part A, we have the person at point A. They're falling down. This looks like a potential energy turns to kinetic energy sort of problem, where we've got M1, G, how far are they falling? They're going to fall this distance, which is L. So we can get V is the square root. M1 disappear to GL. So far, so good. Part B, the tension in the rope just before we collide with the object. Okay, so similar to beforehand, we have 2 forces on this rope. Tension going up, gravity going down. The sum of those forces must equal MA. Tension's got to be bigger. And we're going V squared over L, or V squared over R, radius, which is the length here, to make that work. So the tension must be equal to M1G plus M1 times 2GL over L. So the tension is 2M1G plus M1G, so 3M1G is our tension in that line. All right, part C, the speed of the person and the object just after the collision. All right, so they finally mentioned the word collision here, which what I teach my kids, it's a clue. This is P before equals P after. So this is P before equals P after. So this is going to be mass m1 times speed, which is square root of 2gl, plus 0, because m2 is just hanging out there doing nothing, is equal to m1 plus m2, because they grabbed onto the rock, and then v2, because I already used v above. So let's just, we just divide, right? That's all it is. So this is our velocity must be m1 square root of 2gl over m1 plus m2. All right, and there is that part. And since we've got a few minutes left, let's go ahead and do P as well, just for the sake of it. This part is probably more messy than you'll see on the AP1 exam, but it could work. It's all possible here. All right, so we're looking at falling B to D. We're looking at some kind of projectile motion. All right, we're looking at the total distance x here. Total distance x happens to be L until this point, plus whatever value this is while they left until they hit the lake. So we've got to find two parts here, or find the D part and then add them together. So projectile motion, first step, we need to figure out the time we're in the air for. That is just using the vertical information. So yeah, that could work pretty well. So part one, we want to find time. We're going to use y equals y naught plus v naught yt plus 1/2 gt squared. We have to follow the distance of L. We aren't moving at the beginning vertically. All our motion's horizontal, so that's easy. That's just 1/2 gt squared. T is the square root of 2L over G. And there's our time. Now we get to go ahead and let's find, what do I call it, capital D, the distance we went from the edge of the cliff until point D. Well, that's just using x equals x naught plus v naught xt plus 1/2 at squared. All right, so x is what I'm looking for. We're not starting anywhere special. We do have a velocity, right? We have a velocity of this mess of a thing, m1 square root of 2gl over m1 plus m2. That's my velocity. My time is the square root of 2L over G. Okay, so this looks like we're going to cross off some things here. The square root of G and the square root of G can cancel. And square root of 2L times square root of 2L is 2L. So that means x is m1 times 2L over m1 plus m2. And that means, I'm sorry, that's D. That means our total distance, the answer to part D now, is going to be taking that and just adding them together. So we will say the total distance is equal to L, because that's what it was from points A to point B, plus 2m1L over m1 plus m2. And there's our answer to that part of the problem. Okay, and on that note, since no one is here to answer questions, we're just going to call this stream good. If you guys have questions or concerns, open Q&A next Wednesday. Come with questions, and we'll do our best to answer them. All right. Thank you guys. Have a great night, and I'll see you all next